So this is our 8th and final problem session. Next week we'll have a review session where I'll go over last year's exam. It's been posted, but I don't have a room booked for that yet, so look for my email. This week's we're looking at input-output feedback linearization, and it's pretty straightforward. So I'm gonna do two examples and that are not the homework, but essentially illustrate the same thing. But first I want to just have a look at homework 6 a little bit. So in problem 2 of homework 6 we had the equation that was Van der Pol equation. And the question asked to use the second method of Lyapunov to find whether the origin is stable or unstable. And so what you did was, you found a Lyapunov function that looks something like this. And then you took the derivative, and that gave you this. So we can expand that. So when x is less than 1, so when the magnitude of x is less than 1, can you guys tell me if this is positive definite or positive semi-definite? Not sure? Positive definite? So what's the difference, right? Positive definite is when this function is positive everywhere except when x and x dot are both equal to 0, right? And positive semi-definite means that this function v dot could be 0 at another place other than the origin. So for this case, you see that if we have x dot is 0, then it doesn't matter what x is, v dot is 0. So we have v dot is positive semi-definite. So in a case like this, when you're asked to kind of say whether it's stable or unstable, so in the first part of the question, you already showed that the equilibrium was unstable. Over here we have a v dot that's positive semi-definite, and there are some theorems of instability in Slotine. If you look at section 4.3, but these theorems only apply. One of the conditions for these theorems are when v dot is strictly positive definite. When this is the case, you can find a region of instability. When we have a case like this, we can't really apply these theorems, so we can't really make any claims about the region that it's unstable. So that's the point that I wanted to make here in this question, because a lot of people, most people in fact, said that when x is less than 1, then we can say that it's unstable, and it's technically true, except from this analysis we can't make that claim. We only know that because we can simulate it. We can draw the phase plane and see that there's a limit cycle and stuff. So over here we can't make a claim about the region. The second point I wanted to point out was a lot of people said, well, if x is greater than 1, then this becomes negative, right? So this becomes negative definite, and then v dot is less than 0, so when x is greater than 1, it's stable. Now this might make sense intuitively, but if we so it's true that there's some sort of limit cycle over here, and that everything outside sort of converges to this limit cycle. However, when we're doing the Lyapunov second method, it doesn't really it can't really handle cases like limit cycle. That's why we have the invariant set stuff. So when we're doing second method of Lyapunov, we're only looking at stability about equilibrium points. And if you recall the definition of stability, it was, an equilibrium point is stable if for any big R greater than 0, there exists some small r greater than 0 such that when we start inside the small r, then we will remain in the big R for all time. More specifically, this definition means that we can make R as small as we want. Okay? So that means if we have some region, big R, we should be able to make that big R as close to the origin as possible, or as we want. And we would still be able to have another small r that's inside it, and our x of t will never leave this big R. So when we have an unstable equilibrium, you can see that this doesn't really apply because it's like our origin has a hole in it. Right? So we can't actually use the Lyapunov to say that when x is greater than 1, it's stable, because it's not, because the Lyapunov only looks at equilibrium points, and the equilibrium is unstable. So that was my second point. Any questions on that? All right. All right, so for today, I want to look at input-output feedback, linearization. The first example I'm going to do is how not to control an aircraft. So let me just draw an aircraft here. So this is our wing, this is our tail, and we have an angle of attack. Here we have our center of lift, and let's say our CG is somewhere up here. And call this distance d. And here we have the tail is also producing some lift, but it could be in the downward direction. Call this angle E for elevator. Call this distance L. So this example is trying to use the elevator to control the altitude of the airplane. So if we write our equations of motion, I'm not gonna go into detail, but for our rotational equations of motion, we have some moment inertia about the CG. So alpha double dot equals to, say we have some aerodynamic torques like drag, that's producing a torque about the CG. We'll call that some constant beta times alpha dot plus, alright, we're going to have the lift be a linear function of alpha, and we're going to have the lift of the tail be some other constant c, so e times e minus alpha. So here, if we're taking moments about the CG, you could see that there's some. You have the aerodynamic torques, and you have this lift, which is in the positive alpha direction, and that is c e times L. And then we have this producing a torque, the lift producing a torque on a CG in the negative direction. So we have C times D. So just rearrange that. And for our other equation, so our force balance, we can have simplified. So this is, assuming small angle approximations and all that stuff. So basically what we're saying is the acceleration in the vertical direction is a function of your angle of attack. So if we put in some numbers to make it easier, J is M, these are all ones, it's 4, C set W is 5, L is 3, D is 6. So now we can, so there's two ways we can go about this. The first way is we could do the classical control style and write some transfer functions between our H and E and alpha and E. We can do that later. What I'm going to do is define our state vector to be alpha dot, H, and H dot. Okay. So this is x1, x2, x3, x4. And that gives us the following. So x1 dot is alpha dot, which is x2. x2 dot is alpha double dot, which is that equation up there. If we sub in the numbers, we get negative 4 x2 minus 4 x1 plus 3 is our elevator. x3 dot is x4, and x4 dot is our second equation, which is 6x1 minus e. And the y that we're interested in is the altitude h, so that's x3. So now we can apply our input-output linearization. So the first step is we differentiate y until this e, which is the input we're used to seeing u. So until that appears. So we can do y dot is x3 dot, which is x4. Okay. Doing it again, y double dot is x4 dot, which is 6x1 minus e. Okay. So we did it twice, and our e appears. So that means our relative degree is 2, right? So now we can begin by designing our controller for E. So I'm gonna, at this point, just make that a U so everyone is on board. We can say that U is U1 plus U2. We can say that U1 cancels out our dynamics. So let U1 be, so here we have a minus, so U1 is just 6x1, and that'll cancel out the other one. For our U2, we can now choose some aerodynamics, right? Let's say we want to put all of our poles of the aerodynamics at -1, right? So we end up with an equation in terms of our error that looks something like this: E double dot plus 2E dot plus E0, where E is y minus y desired. Okay. So if we just write that out, this gives y double dot minus y double dot desired plus 2E C0. And so once we cancel this y, we have just y double dot is just minus U2. So now we can put this in, and we have minus U2 minus y dot plus 2 dot plus e is 0. So our U2 is just minus y double dot plus 2 dot plus e. Putting everything together, we have U is just 6x1 minus y desired double dot plus 2e dot plus e. U. So all these problems have a pretty standard formula. First, you differentiate y until you see u, and then you design u. That's the second step. And the third step is to see if there are internal dynamics, make sure that they're stable. If they're not stable, then your controller is not going to work because something's blowing up. So let's have a look at our internal dynamics. What are our internal dynamics in this model? Any guesses? So this is the equation that we used, right? To basically design our U. And here you see it also appears. Right? And we haven't used that at all in here, right? When we're designing it. So this x2, which is the alpha, that becomes our internal dynamics. So we haven't seen it. So if we write that out, x2 dot is negative 4x2 minus 4x1 plus 3 times 6x1 minus y double dot plus 2 plus e. So when we're checking our internal dynamics, I think, so for example, in your homework, you should check both of these, right? And one of them, if you check this one, you will end up with exactly this error equation, which is to be expected, right? So you could say that one is stable. Here I'm gonna skip that part. I'm only checking the second one. So when we do this, we have x2 dot equals to minus 4x2 minus 4 plus 14 x1 plus 3 times this stuff. So if we just move all of this stuff to the other side and then sub in the alphas and alpha dots, you can see that we get alpha double dot plus 4 alpha dot minus 14 alpha equals to this stuff. Right? So is this stable? Turns out it's not. Turns out that the poles are at negative 6.4. So our internal dynamics is not stable. Now this happens to be a linear system, which is really easy to see whether or not it's stable or not. But when you have a nonlinear thing here, it could be alpha cubed or something. Then you would have to use all of the Lyapunov techniques. Find the v and see if v dot is negative definite. Then you can use that for the stability of this part. So our alpha is unstable, so it blows up. Now I actually put this into Simulink and simulate it. Unfortunately, I can't show any plots. But what happens is we can track so for an airplane, you might know this. If you apply the step input to the elevator, it generates a downward, a lift in the downward direction, right? Which rotates the plane, and then it goes up, right? So when you're putting in that step, the height of the plane actually, goes down before it comes back up. So this is what this effect is basically a 0 on the right half plane, so an unstable 0. For this controller, what we see is, we could control H beautifully, right? When I simulated this, the response looked like something like this, right? But then our alpha just kind of blew up, and as soon as it leaves this tiny region, remember this is a small angle assumption, and now the linear stuff doesn't hold, and our whole thing equations break down. So this is not what you would do when you control an airplane. Any questions? Okay. So the second example is from a final exam a couple years ago. Huh?
Was this example?
This example is actually in Slotine. I just found it's thought it was a pretty cool. So the second example, you're given the equations x double dot plus 2x dot minus x cubed is u, and y is x dot. So design input-output, feedback linearization for u. So the first part asks you what's the relative degree. If we're given an equation like this, the first thing we do is put it into states. Right? So we could have let our x1 be just x, x2 be x dot. So we could say x1 dot is x2 and x2 dot is minus 2 x2 plus x1 cubed plus u. So our y is x2. So we start taking derivatives. Y dot is x2 dot, which is minus 2x2 plus x1 cubed plus u. So u appears. So that means our relative degree is just 1. Second part is to design a control law, u. So we have it into this form, and once again we cancel out all the dynamics here. U equals to u1 plus u2, and we let u1 be 2x2 minus x1 cubed. Cancel this part out, and we're just left with y dot is u2. So now we can define some aerodynamics. Let's say we want to put our error at just the poles of our aerodynamics at -1. So we can have E dot plus E at 0. Where E is y minus y desired. again, we have y dot minus y desired dot plus y minus y desired 0. U2 is y dot, so we can just sub that in. U2, and if we move everything onto the other side, we get U2 is y desired dot minus y is x2 and plus y desired. So there we go. So that's our controller. The third part asks for what are the internal dynamics of the system, and will the design return the system to the origin from all initial conditions. So here's our system. What are the internal dynamics here? Do we have internal dynamics? It's a trick question. Yes, we do have internal dynamics. Because our relative degree is 1 and it's a second order system, so we must have 1 degree of internal dynamics in here somewhere. So in designing the control law, we were using this equation. So we could substitute u back into here, into the second equation, and we would end up with this error equation. And that shows us that the dynamics for x2 is going to be stable, and it's going to follow this error equation. But we still have this first equation, which says x1 dot is x2. What does that mean? So more importantly, can we use this design, this control law, to return the system to the origin? What do you think? So let's have a look at, if we pretend these are positions and velocities, right? Our y is our velocity. So that's the output that we're looking at. This over here is just it's an integrator, right? It says integral of velocity gives you position. But if we define our output as the velocity, and we're trying to zero out our output dynamics, so over here we have E dot plus E is 0. This means that we can make the error 0, right? And the error is y minus y desired, which means we can make our velocity 0, right? But does that mean we can make our position 0? No, right? You can't. If you think of this as a measurement, right, a sensor measuring the velocity, if you're just measuring the velocity, you don't have any idea of the exact position you are at, then you will never be able to find the origin, right? How do you know where it is? So the answer is no, you won't be able to return this system to the origin from any initial condition. Is that clear?
Was that the goal of the problem? To return
Yeah, the goal is, the problem asks, will this design be able to return you to the origin?
okay. And no, because what it's doing is returning your velocity to zero.
Exactly. Okay.
So to find the internal dynamics, we just plug u back into x2 dot.
Yeah, so there's, to find the internal dynamics, you essentially take all of your equations and you plug in u wherever you see u, and you try to see if that equation is stable. So for instance, this one where there's only one place where u shows up, so we plug this in, and since we use this equation to design our controller, we're going to end up with this exactly. If I were to say that there's another u here, right, then for this internal dynamics, you would also have to plug u into here and then see if that's stable.
So is it not possible to find the internal dynamics here?
So these are the internal dynamics. So, and it's like s times is x2, right? Which is, so then x1 over x2, which is like just 1 over s. Right. So it's just a single integrator, and it makes sense if you think about it in the position and velocity.
So it's stable, it just won't, it won't be back to the.
Yeah, you can think of it that way. It's in.
So even though u has like a y, oh I'm sorry, y, so y desired is actually the velocity. Okay.
But if you wanted, you could make this explode, right? While keeping, like with a finite u, you can drive this to infinity, right? Because what we're saying is, we're controlling the velocity, right? We can put in, if our desired velocity was some bounded value, then the position, right, is just going to keep going. Right? Okay. Any other questions? So all the problems are essentially, they follow the same formula. All right. Well, that's it for today. Thanks.